My name is Mason Walters. I'm a senior principal with Forel Alcesser Structural Engineers in San Francisco. And being a practicing engineer, they don't let us out very often. So it's kind of nice to get over here and we think we know the state of practice, but then to find out what the beyond the state of the art is and looking forward and future directions is really super interesting. As is some of the conversation that I have with the different speakers and people here, and I'm always impressed with the depth of thinking and investment that goes into risk evaluation, mitigation, and for all types of natural and man-made hazards. So this has just been a great conference for that. So anyway, we're glad you're here. We're in the home stretch. This is really the last session, and we have three speakers. And so for the first hour, it's going to be their talks, and it'll be followed by up to a half hour of interaction with the audience. There'll be a microphone. There is a microphone on the floor. We'll have the speakers up here. You can ask questions and be sort of like a panel discussion. So I have the privilege of introducing today three really apparent overachievers. These people are really have such long backgrounds I can't possibly even get into them. But I will start with David McCallen. David is a professor at University of Nevada, Reno. He is the director of the Center for Civil Engineering Earthquake Research at UNR, and somehow manages also to be a senior scientist at LBNL, where he leads the EQSIM Exascale computing project. So he's really steeped in evaluation of structural systems with high-speed computing, and that kind of research is very interesting to me as a practicing engineer, but probably a lot of people here. So with no further delay, David McCallen.
Thank you, Mason. Let me add my voice to the chorus of kudos to Pierre. I come to this meeting periodically, and I always learn something, and I often learn many things. And the last 2 days have been emblematic of that, so kudos to the whole Pierre crew for another excellent workshop. You heard a little bit yesterday, a couple of use cases of what I'm going to talk about. Artie Rogers talked about advanced simulation for earthquake ground motions, very nice presentation. And Maha talked about utilizing ground motions and reinforced concrete models. Turns out both of those activities have a link to what I'm going to talk about for the next few minutes. And I am going to sort of go to a higher level and talk about the earthquake simulation project we're working on for the U.S. Department of Energy. This is a combined effort by Lawrence Berkeley National Laboratory, Lawrence Livermore National Laboratory, and the University of Nevada at Reno. And the appearance of those different organizations will become clear as we move forward. I wanted to begin by talking about what I think is a tremendous success story that is often not recognized. We all sort of take it for granted. What I'm showing in this plot is the world's #1 ranked supercomputer starting in the year 1995. And so everything here, I guess the first thing you notice that's apparent is that this slide goes up and to the right. The computer science community and the hardware community have done a tremendous job of overcoming roadblocks in the advancement of high performance computing. We started with mainframe computers, then we went to vector machines like the Crays in the mid-'80s when I was a graduate student and arrived at Livermore. And then finally, as we got into the 90s, driven by the DOE and the ASCII program, we began to do massively parallel calculations on massively parallel machines. So it's really been a tremendous increase. When I started in 1982 at Livermore as a graduate student till today, the performance of high performance computers has increased 12 orders of magnitude. And there are not a lot of things in nature or anywhere else that increase in the built environment with that a degree of increase. So it's really quite tremendous. So DOE ushered in the area of high performance computing, and really the last few years we've sort of begun to get to a spot where things are bogging down and not proceeding quite as fast as people would like. We've gone to many nodes loaded with many cores, and we've sort of maxed out that architecture and so forth. So DOE has picked up the mantle to do the next major push in high performance computing, and that is called the Exascale computing program. And I've indicated it with the blue box there. Where do they want to get to? They want to build the first Exascale machine by the year 2023 and have it operational for science. Actually, they want to build 2 of them. The way DOE operates is they will build 2 machines to accomplish the same task with diverse architectures in case one of the architectures fails. It's a risk reduction activity. So that's really where they want to get to by the year 2023, and it's going to be a tremendous national investment. And as you see in the upper right-hand corner of this slide, they're on track to spend $1.8 billion in terms of this effort. And be mindful, an exascale machine, if you can fathom this, is a billion calculations per second. It's kind of getting hard to even grok this though. So the components of this program overall are threefold. Number one, on the right-hand side, is to build exaflop computers. And as Artie Rogers alluded to yesterday, it's going to be a fundamental change, most likely in the architecture, where we'll be less reliant on CPUs and more reliant on GPUs, graphical processing units, to actually do the scientific calculations. DOE is somewhat inverting the process that they've done historically going forward here. Typically, they would build a supercomputer of one of the national laboratories, and they would spend the next 2 or 3 years getting the software to catch up with that architecture and moving codes to that architecture. It's a big deal to move some of these new machines. They have sort of flip-flopped that with this current program, and as you'll see, they've put 2 upfront activities on the left that are going to be executed to prepare for the exascale computers. One is software technology, where they're going to be developing a whole software stack, I/O, advanced I/O, advanced MPI, advanced equation solvers, all the things we'll need to draw from to operate on these machines. Secondly, in a competitive sense, they had a call for proposals, and they selected 24 application developments to get ready for exascale computers. Turns out that we submitted a proposal through Berkeley Lab in collaboration with Livermore, and we won, were elected and selected for one of those applications. And so what did we propose? And be mindful that part of the criteria for judging these were applications that really demanded exascale computing in a big way and demonstrably so. So we came up with an idea to sort of have an ambitious proposal to do simulations of earthquake phenomena all the way from the fault through the earth and finally to the structure. And we called that the end-to-end fault to structure simulation, and that's the proposal we tendered. Really, we argued about 2 outcomes from that. Number one, things we'd like to explore once we develop this framework is how do earthquake motions really vary in a region, across a region. We know it's very complex from observations. We know these ergodic ground motion models can't capture that really local variability, so that was one of them. And for engineers, another important one was how do earthquake incident motions really interact with the structure when they arrive at that site. For years, we've made a lot of idealizations. We take a motion at a point on the Earth's surface, and we apply that in a fixed-base sense to our structures. That's only true explicitly if that ground motion, the way we apply it, comes from pure vertically propagating compressional waves and pure vertically propagating shear waves. That's not right either. So we would like to explore those types of things. This is a multidisciplinary problem, kind of takes a village. We have a good budget. We have people in structural mechanics. We have people in seismology and geophysics, so the disciplines are on the left. On the right, honestly, are the real heavy lifters in this project. Our milestones tend to be demonstrating the high performance computing, as I'll get into. So the applied mathematicians and the computer scientists that really know how to make these advanced architectures swing are really an important part of this. So why is this an exascale problem? Well, seismologists, I love seismologists, I love Artie. They've been in the realm of calculating low frequency motions for a while. We really want to push these calculations to be more relevant to engineering structures which is a lot higher frequency resolution. So that's really the heart of why this is an exascale problem at a fundamental level. We want to get up to be able to compute all the way from maybe 2 to 10 hertz of ground motions in that frequency range. So what do we have to do that? We have to run much, much larger models much faster. Already mentioned yesterday that doubling the frequency resolution with standard traditional uniform models leads to about a 16x capacity or need in computation. So it's a very, very stiff curve to go up to. Number one, we want to run many realizations. We don't want to just do one hero calculation. We don't know how the Hayward fault's going to rupture a priori. We don't know whether it's going to rupture at the hypocenter at the north, rupture towards the south, or vice versa. So we want to be able to run a lot of fast realizations. And finally, representing the fine scale geology, there are limitations in our subsurface models, and I'm not going to have time to get into this today, but we have some remedies and software we're developing to deal with that as well. So for exascale problems, they don't just drop a pile of money in our lap and say, go do good things. In this program, you are under tremendous scrutiny. You have to define your exascale problem very explicitly, and we track to that problem and have to report our progress and our figure of merit very frequently. So the problem we selected to exercise our exascale codes is shown here. We chose the San Francisco Bay Area. Already talked about this yesterday, a zone that is about 120 kilometers long by 80 kilometers wide by 30 kilometers deep. And when we turned in our application, we said, this is what we're going to do. We are going to start from traditional historical performance in the upper left-hand corner, where on the vertical axis is the compute time in hours for a Bay Area model, and on the horizontal axis is the frequency resolve. We're going to start up there. We're going to shoot for a 5x increase in our frequency resolution and a 5x decrease in our solution time. So we're going to try to calculate a 10 hertz run in the Bay Area by 2023 in about 5 hours. So that was a very ambitious goal. So doing a number of things to get there. We're starting with the SW4 finite difference code that was originally developed by Anders Peterson at Lawrence Livermore National Laboratory. It is a summation by parts, fourth order code in space and time. Anders is an applied mathematician. He's very picky. So everything in that code is demonstrably checked out in a very, very rigorous mathematical sense, which is one of the reasons we selected that code. We've been busy for the last 2 years doing a lot of improvements in that code to get to where we need to get to. Already had mentioned briefly that we use in this code the finite difference grid is Cartesian at depth, and it's curvilinear near the surface. We have been working on optimizing the zonation of that model to be copacetic and optimized to the properties of the Earth. We've put in stochastic geology. Arvind Pitarka has a spatially varying stochastic geology model. We've put in a new rupture model, Gray's Pitarka model, that includes a stochastic component as well as the ability to put in deterministic asperity. So we've done a number of things to improve this model. Everything we do has to be couched in the framework of we're trying to get to models that run 300 billion grid points. And so we have to be computationally in tune and efficient with every single thing we do. We can't be sloppy. So it's a bit of a challenge. Computer science is crucial in this. We don't know today precisely what the architectures are going to be in the exascale machines when they get here. So we have to be a little presumptive. Probably the best analog is the #1 computer in the world right now at Oak Ridge. We're running on the Oak Ridge computer. I'll show you some examples. It's a 200 petaflop machine with a lot of GPUs. And so the computer scientists work and applied mathematicians to tell us the best way to divvy up that model and distribute that amongst the nodes of the computer. And we have a paradigm that we call pencils. We divide that domain up into vertical columns that discretize through the depth. And we distribute that out across all the nodes to run the problem and bring that all back. So we've done a lot of work. We've made great progress. In my view, I'm going to show you those performance curves. Recall we were going to start there and end up there. Every single curve and block you see there is a Admiral's test run that we have made in the last 2 years to judge our advances in performance. And those are performance curves that vary as frequency to the fourth. So you can see how steep and how hard it is to get to the right. We started on the Cori platform, a 30 petaflop platform up the hill. At A, We had algorithm and platform optimizations. We got to D. That was the summer of 2018. About that time, I'm saying, oh no, what did we promise? Because we were a long ways from the promised land. Then we got access to the world's fastest machine. And we ran the next case on Summit, and we jumped over to E. Tremendous increase from the hardware. So it gives you an idea of how we are planning and striving to move across here. So the run on Summit, just to be clear, was the largest one we've made is about a 10 hertz run, was a 10 hertz run. Number of grid points in our Bay Area model, 203 billion. Smallest size of the element near the surface, 6 meters. We used 1/4 of the machine, because that's all they would give us. So we had to look at what we would scale to if we got access to the whole machine. Based on the strong scaling observed on Summit, we would get to a 10 hertz run, 4,800 nodes in about 7.6 hours. That's not bad. This slide has caused me a lot of grief in our reviews because the computer scientists keep saying you're there. Well, I point out to them we're not there. We want to get to a shorter runtime, and this is only with a V sub S of 500 meters per second. We know based on analyses that we've done in a paper in the BSSA that we have, you've got to get to lower velocities to capture the hazard in the Bay Area. Not surprising. So we've made great progress, but we're not there. So what about the coupling to the engineering? So we have defined two modalities of coupling, what I characterize as weak coupling and strong coupling. In the weak coupling, we take the motions from the geophysics model, just like we've done traditionally. We take the motion at the surface and we feed that into our fixed base model, just like we've always done. The only perturbation we have here is that we can put in rotations too. We can put in ground rotations, particularly if we think about sites close to the fault. And if you've looked at the paper of Tafunic and others through the years, you know that there's a belief that rotations in the near field are important to determining the drifts in the building. So that's our fixed base case. The other case is we use BLAC's domain reduction method. We take the SW4 motions on the boundary of the included fun element model and allow those to go into the model in an appropriate way. That captures SSI. It allows us to look at soil structure interaction. More importantly, it allows us to look at complex three-dimensional incident waveforms. No longer I need to make this assumption of pure vertically propagating shear and compressional waves. So it allows us to explore that space. This spawns two types of workflow for these. Number one, on the top is we run our SW4 model, we save all those surface motions, and we take our model out of our library, and we have a number of steel frames, contemporary steel moment frame models of different heights, and we're going to have Maha's reinforced concrete models shortly, and we say, I'm going to put that model in every node of your grid, and I'm going to analyze that building to see how the risk varies for that particular structure regionally. And you can see it's quite complex. The second mode is to define where we want to do a very detailed soil structure interaction analysis and look at the incident mode, complex incident motions. We define a domain around that soil island, and we save those motions and interpolate those to the domain reduction method to the boundary and analyze the structure. So we can now, the first workflow, we have sort of got that whipped. We can now execute models at least to 5 hertz on a fairly routine basis, and you can sort of see for a 40-story steel moment frame and a 9-story steel moment frame, pretty darn complex variability of motion in our current Bay Area model. We try to scrutinize these models and confront them with data at every turn, every opportunity. Already talked about comparing statistics of our models to ground motion prediction equations. I think in my mind there are two ways of looking at these models and judging them. One is just simply qualitative. Do these models create waveforms that match reality in some sense? And I think in large part the answer is yes. This is a near field site. You see with a strike slip magnitude 7 earthquake. You see on the top there, the displacement on the ground. You see a nice step function because of the fault offset. And on the bottom one, you see a nice fault normal displacement pulse, which is I think realistic. We try to confront these with data. We're using some data that Baker assembled at Stanford of near field motions. We have constructed a relatively simple fault, magnitude 7 fault, One of the beauties of a simulation model is we have 4,000 stations on that domain. So we take 800 stations that are close to the fault, we analyze our building, and we look at the distribution of what the peak interstory drift is in that domain. Then we take those real motions and we repeat that for the same building. And we ask ourselves, do those drifts look the same? And by golly, a lot of them look really, really good, just like I'm showing. We're finishing up a document on this right now. When you have 4,000 data points, you need some tools to analyze and interrogate the data and the output. So we're developing some graphics. This happens to be a very, very detailed inelastic fiber model of a 4-story steel moment frame building. I am plotting here the envelope of peak interstory drift according to ASCE 4305 that defines limit states for a steel frame building. And we can play the what if game. We can march out from the fault and look at how the response of the building varies. These are for fault normal motions. And as we move away from the fault and gain some insight, at least from the model, on what it's telling us. This same thing repeated for a 9-story building, and you'll see red here. And so in the middle of the building. So this building, a 9-story for this particular simulated event, gets hammered a little more significantly. We had no experience with the domain reduction method prior to this project, so our postdoc and graduate students at UNR have done a great job. We've assembled a 3-person team, and they have come together and just hammered the heck out of the domain reduction method to convince us that it's implemented correctly and working. And the way we do that is we'll run a SW4 run and look at the ground motions on the surface. Then we will inject, with the domain reduction method, a soil island, run the same problem through the domain reduction method to the boundary, and those should agree if the domain reduction method is working, and they do. We have completed the domain reduction, and this is a SSI simulation of an event 2 kilometers from the fault, and you'll see both vertical motions as well as permanent offset. And so we're able to look at this complex incident wave fields in the near field. I am going to speed up to my 2 last slides. Everything we do, we are wrapping into a practical computational workflow. We've heard a lot about computational workflow the last few days. When you're computing at 2 to 300 billion zones, you gotta be really, really efficient in every single thing you do, because it will expose itself and bog the whole process down if you're not. So we have worked very, very hard on the I/O and being able to efficiently move this simulation all the way from the fault rupture through to the structural response. And so we have a lot of tricky things in this. It's not like you would traditionally do. If you're running 300 billion zones, you don't have a bunch of input files laying around on your computer. What we do is we read the binary data in at runtime, and we create on the fly our input model for that big model, and we run our analysis and then dump the data out. My final slide. What's our end game? And this is where the potential for collaboration. We want to be able, for the San Francisco Bay Area, to run many, many realizations of high frequency simulations. And that goes back to our original 2 criteria. Run to 10 hertz, run it fast. Try to run it in 5 hours so that we can vary the rupture scenarios, we can vary the geology, and then we can look at the statistics of the response for various types of structures and systems. We welcome the opportunity for collaboration. We want this technology to be used. We don't want to spend the next 2 years, 3 years between now and 2023 putting this all together and then say game over. So we would love to engage the peer community and others in opportunities for actually utilizing this and potentially filtering research into this that is done by peer researchers and others. So I'll end with that. Thank you.